Earlier, we showed that if the limit of the quotient of two complexity functions is k, some number between 0 and infinity, then the two functions are in the same complexity category. But if the limit of the quotient is 0 or infinity, they're not. Intuitively, if the limit is 0, g of n is in a slower complexity category. And an algorithm that takes g of n steps will run faster than an algorithm requiring f of n steps. We can formalize this idea by creating a ranking of the complexity categories. Given two functions f of n and g of n, we want to be able to decide which of is true. And so let's think about that. If g of n is order f of n, then for sufficiently large n, g of n is sandwiched between two multiples of f of n. This means regardless of the size of n, executing g of n steps will take at most c2 times as long as running fn steps. But if hn is in a different order, then for any c for sufficiently large n, we'll have hn greater than or equal to c f of n, or f of n greater than c h of n, but we'll assume this direction of the inequality. So remember, concrete never hurt, so let's take a specific case. If we know that g of n is order f of n, we might have g of n somewhere between 100 f of n and 100,000. And regardless of the input size, g of n will never take more than 100,000 times as long as f of n. So if f of n steps can be executed quickly enough, so can g of n steps. But suppose h of n is not in the same order. Taking c equals to 1,000, and we have, for sufficiently large n, h of n greater than 1,000 f of n. Consequently, for large enough n, h of n will take at least 1,000 times as long. Now, could we build a faster computer? And the answer is no. Suppose we could, where the 1,000-fold increase in time is negligible. Since that constant multiplier isn't fixed, it's true for any value of c, we'd also have cases where h of n takes 1,000,000 times as long, or 1,000,000,000,000 times as long, or a lot longer. So no matter how fast the computer is, there will always be problems that take an arbitrarily long amount of time to complete. So now let's consider f of n and g of n. If g of n has order f of n, then g of n is big O of f of n. But we also have f of n big O of g of n. That's because since g of n is order f of n, then g of n is omega of f of n. So there's some c where for all sufficiently large n, g of n is greater than or equal to c times f of n. But this also means 1 over c g of n is greater than or equal to fn, where 1 over c is non-negative. And so that means that f of n is less than or equal to some constant multiple of g of n, and so f of n is big O of g of n. And this suggests a way to order complexity categories. Suppose f of n is big O of g of n, but g is not big O of f of n. Then the complexity category of f of n is in some sense smaller than the complexity category of g of n. For example, we can show that order n squared is smaller than order n cubed. Now, clearly n cubed is theta of n cubed, and n squared is theta of n squared. And intuitively, we'd expect n squared to be big O of n cubed, but we should prove it. We note that for large n, say n greater than or equal to 1,000, then we have, and so n squared is smaller than constant multiple of n cubed, and so n squared is big O of n cubed. Now, if we want to show that n cubed is not big O of n squared, so suppose it is, so that there's a c that, for sufficiently large n, we have, then n is less than or equal to c, so consequently this c only works up to certain values of n. So n cubed can't be big O of n squared, and so by our definition, the order of n squared is in some sense smaller than the order of n cubed. So if the limit of the quotient is k, where k is some positive real number, then g of n is order f of n. But what if the limit is 0? Intuitively, we'd expect g of n is a slower function than fn. In other words, the order of g of n is smaller than the order of f of n. Well, let's prove it. Suppose our limit is 0. For any epsilon, and for all sufficiently large n, that quotient has to be less than epsilon, and so g of n is less than epsilon f of n, which means that g of n is less than f of n, and so g of n is big O of f of n. So now we want to show that g of n is not omega of f of n. Well, suppose it is. Then for any c, and for all sufficiently large n, but for any epsilon, and for all sufficiently large n, so for any c, and any epsilon, and all sufficiently large n, g of n is sandwiched between these two functions. And since f of n is a complexity function, it's non-negative, and so we have our quotient sandwiched between any c and a very small value of epsilon. But we can choose c and epsilon to make this false, and so g of n can't be omega f of n. And this gives us a useful result. Suppose f of n and g of n are complexity functions and their quotient is L. If L is a non-zero finite real number, then the two functions have the same order. But if L is 0, the order of g of n is smaller than the order of f of n. Now, a useful idea is to consider the corollaries. And in particular, we don't know what happens if the limit is infinity. So suppose the limit is. Then, if I take the reciprocal, that limit will be 0. And so the order of f of n will be less than the order of g of n. And so our corollary tells us what to do if the limit is 0. This leads to several useful simplifications when trying to find the order of a function. Let's start with polynomials. If f of n is a kth degree polynomial, then the order of f of n will be, well, let's find that limit. If f of n is a kth degree polynomial, we can express it as, and we can rewrite that quotient individually as, and as n goes to infinity, we're left with, which is some constant, and so the order of the kth degree polynomial is the same as the order of n to the k, so we can ignore all but the highest degree terms. What about power functions like n to the 8th or n to some decimal or fraction? So suppose p and q are positive with p less than q. Let's look at the limit as n goes to infinity of their quotient. While we could use L'Hopital's rule, let's avoid the copay because we can simplify algebraically. Since p is less than q, then we can simplify our quotient as, and our quotient is going to go to 0. And so this proves that if p is less than q, then the order of n to the p is less than the order of n to the q.